All right, what's a rational function? These are all definitions. Nothing too crazy. So a rational function is pretty much where you have a, your f of x equals some function over another function. We'll call it p of x over q of x, where p of x and q of x are polynomials. And we're going to get to it soon. We did a whole section on these. Remember, these look like the ones with the hooks, and these are the ones with the asymptotes, and we have to decide where there's a horizontal asymptote, where there's the vertical asymptotes. We did a whole thing on that. We're not going to go there today, but we will eventually. Yay! But just keep it in the back of your mind. We got a lot to do with rational functions and what they look like and fun stuff like that. Then there are root functions. And root functions are like f of x equals x to the 1 over n. Well, and that really is the nth root of, x, the nth root of x. So again, these all have special things going on with them. The domain for this is where your domain would be where this is defined. Same thing up here. Your domain for a fraction is where it's defined. So we're about to do that again, because this is a very important concept. So you're going to be like, I thought you already told us this. I did. And I promise you, I do teach it again last year twice, because it's very important. It's very important. What do you have tomorrow? So it's very important. What do you mean? I still am confused. Find the domain of the following. And I'm going to give you these types of functions in here. So we'll do this one. We'll do no functions. You've got to know the domain. The domain is where it's defined. Where am I defined? And again, we have problems when we're fractions. Where's our problem at? In the denominator. So where in this denominator, where can I not be 0? Where is it going to get me 0 at? You should probably already know it right now.
1 and -1.
1, -1. Like, so if you factor this out, you get x minus 1, x plus 1. So 1 and -1 are your problems. So then your domain would be, and I think Liam asked this question before, your domain would be then from -infinity up to the first problem, which is -1, united with -1 up to the next problem, 1, united with what?
1 to infinity.
Okay, and again, notice they're not closed because we're talking about domain, and you don't want to be -1 or 1. You want to get really close to it. So look for the bottom. We don't want the bottom to be 0. We talked about that in fractions, okay? What about this domain? Is it going to be 0?
No.
No. If you set this equal to 0 and try to solve it, right, you get -4/3. You take the square root of a negative. Is that true? No. Okay. So this isn't going to be 0. You can graph it yourself and you can look for it. There's the domain for this one is all reals. Okay. So that can happen also. All right, so let's take a look now at these root ones. What happens with the root? Okay, so we talked about the root. Is the root under a square root? Let's start there. Under a square root, are you allowed to be 0? Can you take the square root of 0? Yes, you can. Can you take the square root of a negative? No. So you want this to be bigger than or equal to 0. If it's a square, or if it's a fourth, or if it's a sixth, anything that's even, you want it to be bigger than or equal to 0, okay? So what would this be? This would be 4 is greater than or equal to 3x. Let's see, 4/3 is greater than or equal to x. How do I write that with correct notation? Domain would be, actually read this backwards. X is less than or equal to. So what would be the biggest number? I need to write this backwards. Less than or equal to 4/3. Yeah. So how do I write that in correct notation? What's the lowest that x could be? Negative infinity to where? 4/3 with a bracket. Okay, that one is bracketed. And you'll see if you graph that on your calculator, you'll see it shoot over, and that's the direction it will go is actually flipped. So you'll see that all the domain could be coming from the left-hand side. All right, now this one, cube root. And we've talked about this before. If you're a cube root, do you have issues with 0? No, you can take the cube root of 0. Do you have issues with positive numbers? No, you can take the cube root of 2. Do you have issues with negative numbers? No, you can take the cube root of -8. Did you know that? What's the cube root of -8?
2.
So what would be my domain here? All reals. I'd have no problems. Okay?
Because it's disco.
It is disco. Well, it's a sideways disco. Yeah. That's exactly right. Now, if you're unsure, look in your calculator. Your calculator, you'll see it, start to go. Don't always base it on the calculator though, but it's a good thing to do. Please know this. Please make sure you go over this. This is important. I will put it on quizzes. And the reason it's important is because we have to start doing continuity, and then we have to do limits, and there's all these issues with domain and all that. So that's why I kind of hone in on this. All right. Another definition that I actually never used last year, but we did a lot of, they're called transcendental functions. I'll be honest with you. I was in Ms. Shields' room and the department head asked me, she's like, so do you do transcendental functions? And I'm like, yeah, totally. Totally we do them. And I'm like, gosh, I don't even know if we do transcendental functions. I couldn't remember because I've never used that phrase, but we do. We totally do. We do. Thank God. I was like, oh dear Jesus. I don't know what transcendental means, but here's what it is. It's nothing crazy. They are functions that go beyond the scope of algebra, which I think is hysterical, that go beyond algebra, like trigonometric. We do those. Trigonometric. Exponential. We do those. Exponential. And good old logarithmic. We do those too. Logarithmic. So just examples of transcendental functions would be, sine of 2x and 2 to the x. Those are just examples. It was just kind of funny. I was kind of thrown there for a second when she told me that. I was like, I don't, yes, we totally do them. Oh my gosh, I don't know if we do them. And I was like, yeah, we do them. Okay. So transcendental functions, we'll get to those. In this chapter, we'll do logs and exponentials. Oh no, I take it back. We were doing trig also this chapter. Woot! So much fun. I meant to say yeet.
Yeah, so cool.
Just say yeet, because that's what my son watches on YouTube. All right, then we have Piecewise. Sketch the graph of the piecewise function. And let's evaluate also, because you got to know that. So where does E go? I really shouldn't have started with that one, but might as well. Do you remember what E is equivalent to, by any chance?
Like 2.
2.7. So would E be inserted into the top function or the bottom function? Into the bottom right, because E is greater than 1. So how do you write this? You would actually just write E minus 2 squared. You could FOIL it out if you want to. E squared, what do you got? Minus 4E plus 4. Like, I'll accept that also, but honestly, you can just kind of keep it there. With E's, I think they throw you a pi tonight's homework, something like that. Just write it, leave it alone. Don't even have to find the decimal. Just write it as is, okay? All right, what about f of 1? Which one does that get evaluated in, top or bottom? The bottom, because it equals 1. So this would just be 1 minus 2 squared. This one, I do want you to get me a real number here. So negative 1 squared is 1. And then f of negative 5. That one obviously would then go to the top. And you would have negative 5 plus 3, which is negative 2. So evaluating piecewise is pretty easy. Now let's talk about how to graph this. I will let you, I will show you how to do it on your calculator again. Actually, I just learned a new way in my Math 171 class at SPCC. I was like, what? I didn't know the calculator could do it all in one. I'll show you that in a minute. It's very exciting stuff. I have to remember it, though, as I'm talking this to you. What is this really, though? X plus 3. This is a what? It's a line. It's linear. Okay, so we know this is going to be a line. And what is this going to be? X minus 2 squared. A parabola. Okay. Last year, I taught you 2 ways to do this. Okay. I showed you that you can make tables and you can then plot the points and see how they go. That's totally fine with me, however you feel. I think you're a little bit above that now because I think you know what this looks like and you know what this looks like. So I think you'd be able, and you know about the shifts. So you should be able to kind of graph it a little bit better now. So I'm going to show you kind of a different way of graphing it, which I think I did show you last year. It's like they're called fences. I know Miss Davis does it that way, so I do like it that way. If we graph here, our problem area is at 1. Would you all agree? 1 is our probably point. We go left of 1, we go right of 1. So at x equals 1, which is right here, I'm just going to put like kind of an imaginary fence. To the left is where I draw the line. Do you all agree, right? And it's an x plus 3 line, so what does that mean? That means you are at 1, 2, 3, and you go up 1, over 1. Oh, should I close that? No. So boo-boo on me. Or you could go down 1, over 1, and down 1, over 1, etc. And you're getting a line that looks like that. So there's your graph. You can make a table of values if you want to, but that's what it looks like. To the right of this line, you have a parabola. That parabola has been shifted where? 2 to the right, correct? Okay, so we know like that the vertex of this parabola is to the right too. So we have 1, 2. And then we know that it's going to go, you know, parabolic shape. But don't forget, you still have to go to this fence right here. I don't call it a fence. So you still have to draw the parabola to the fence, meaning I still need to, you know, plug a 1 in. So if I plug a 1 in here, we already did it. It was 1, so it's right here. And is it closed or open, by the way? Closed. So you actually have a parabola that looks like this. Okay. Now, if you don't like the way I just did that, I mean, it's up to you. Some people would actually draw the entire parabola, then they would just erase, you know, since you're using pencil, I wasn't using pencil, but you can just draw the entire parabola and then just erase from the left of the fence, or draw the entire line and then erase to the right of it. I mean, that's totally fine with me too. But I got to remember how to show it to you. I'm going to show you the old way of doing it, but there's a totally new way and you're going to be mad at me. To graph this the old way, let me move this down. You put this into y1 as a parenthesis. So x plus 3 in parentheses. Then you hit divide. Then you put another parenthesis, put x. This less than symbol is located in second math. It's the logic symbols right there. You see the test symbols right there. So go down to 5 and put less than 1, close the parenthesis. Okay, so it should graph that piece of the line. And then you do it again down here. So down here, I actually don't even think you need the parenthesis, but we are going to put the parenthesis in because we have x minus 2. X minus 2 squared divide, actually I think I'm missing a comma. See, I haven't done this in forever that I can't remember how to do it because I've just graphed them myself. Divide, parenthesis, x, and then go to second math, greater than or equal to 1. Did that graph it or will it confuse? Let's see. There you go. There you go. Okay. If it gives you a statement where it's like 10 is less than or equal to x, which is less than 1, you would actually have to use this logic statement right here, the and you would just put it in afterwards. But there's a totally another way of doing it. I just found out. I have to remember. I can't remember right now. But I was totally blown away this summer when I was like, what? I didn't know how to do this for the longest time. So bummed. I'll figure it out in a minute. I just don't want to waste our time because I want you to be able to get some of this work done. All right, last and final thing is transformations. And I'm literally going to just breeze right through these because I know based on what we just did, you remember these, okay? The transformations of functions. Just write them down because I think if you write them down, they'll, obviously come back to you. Transformations of functions, okay? If you have a function and you add or you subtract outside of the parent, here's where you are at. Outside the parent. Then for this one, you would go up C. For this one, you would go down C. So what I mean is something like, you have a parabola and you add 2 to it, you would shift it up. Here you have a parabola and you subtract 5, you shift it down, okay? So just know what that looks like. If you are inside the parent, so you have your function and you add C inside the parent or subtract C inside the parent. This would go to the what? You do the opposite, left C. This one would go to the right C. That's where the shift occurs, okay? Other ones to remember that I don't think it's probably been a while, but that's okay. If you are outside of the parent and you're negative, as opposed to if you're inside the parent and you're negative, okay? Do you remember what outside the parent negative does? Where do you reflect?
Flips the y.
It flips over, surprisingly enough, the x. Good try though. You reflect over x. So it would be like you'd have this and then you'd end up like this, okay? But this one, you are correct, this one reflects over the y. And, these are my least favorite. I still to this day can't get them and I just don't know why. Jesus help me. I've tried everything. I actually thought I had it this summer again and I was like, yes. No, I don't have it. And like Belky was trying to show me his way. I love you, Belky, but it wasn't working. All I know is that a fraction makes you fatter. That's all I can remember. I know that 1/2 x squared goes wide, whereas 2x squared is a very skinny. And that's how I describe it in my head. Like I'm just like fat, skinny. That's all I say. But they're like vertical stretch, compression horizontally. And I'm like, I have no clue. I just don't know. Fat and skinny, I can learn from that. So, I mean, if you want to help me out, because you know a better way, please let me know. Other than that, I can't help you out. But if this is bigger than 1 and you're on the outside of the parent, gosh, I don't even know how to say it. This is a vertical stretch. If it's a fraction, then it's a vertical compression. Belky was trying to tell me, I think it works. Like if it was y equals 2 sine x, that's on the outside, that's bigger. And I know what sine looks like. The sine curve goes 1, 2, 3, 4, 5. And 2 sine x, right? Wouldn't that 2 is your altitude? I know this is going back and you're like, I don't remember. Just bear with me. It would go up higher. So it'd go boom, 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 boom. It would actually... So is that stretching vertically? Yes, it is, right? Yeah, okay. Belky wins. Belky wins. That one works. But other than that, I couldn't tell you. I'm just like, I don't know. All right, now if it's inside the parent and you're greater than 1, then you have a horizontal compression. So these flip. You have a horizontal compression. If you're a fraction, you have a horizontal stretch. Again, I hate these phrases. I mean, you are more than welcome to put fat and skinny on your test. Because I know what you're talking about. But what it would be is if you're inside the parent and you have like an absolute value, and it's 1/2, it would stretch horizontally. I mean, yeah, I guess so, but I don't like that. So whatever. All right, that's the lesson. I mean, that's it. Yeah. Could you imagine we took forever to do that last year and now we're not? Like,